Okay, so we're going to finish this triple integral by introducing one example on application of a triple integral. Okay, yeah. And then we're going to start a new topic, which is called vector field. So we're kind of going back to vectors. Okay, so we learned triple integral. We learned triple integral, evaluating triple integral using three different kind of coordinate system: Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. Just like double integral, what we should learn is typical applications, okay, of triple integral. So it's actually more useful in terms of this double integral for application, because whenever you're dealing with real world 3D objects, right? And chances are you need to use a triple integral. So what are the typical applications? We're not going to go into derivations here, but just to refer to double integral, what we have first is calculating the mass. Okay, so calculating the mass, the formula is triple integral over the solid region D. Basically, we're talking about mass of solid region D here. And what we're integrating now is integrating basically density, okay, here. So this delta here is density. So that will give you the mass of this 3D object. And we also probably what we need is so-called the average value. So there's a maybe if you recall in double integral we had a so-called average value, okay, of a certain function f, okay, over this region D. So all you need to do is to change the double integral into triple integral. So this is triple integral calculation, but if we divide this term, okay, if we divide this term by this volume of D, okay, we end up ourselves with this average value of f. Okay, yeah, the same concept as we described for double integral. Okay, so if you look at the lecture notes, look at the double integral, you would understand why this gives you the average value here. Okay. An extension of this average value of this one here is so-called weighted average. So weighted average here. The question is, what do we weight this one here? So I can use this concept, use this density as so-called weighted average here. So this f here, instead of dividing it as volume, so you're going to basically here divide the mass, okay, of the D. And the triple integral here is not just simply integrating this function f anymore. So you're going to weight this one here with another function. So let's say, for example, this is a function representing the density here, right? Okay. So that's the so-called weighted average here. So if you have a format like this one here, then you should say, oh, that's sort of like a weighted average of a certain function here, right? Yeah. So as a matter of fact, you can also, if I say this one here, I can also say that's the weighted average for this delta function here, right? Yeah. So same idea. Okay, so then we have this center of mass. Okay, center of mass. So to calculate the center of mass, the same way as the double integral. So x bar is 1 over this mass of D. Okay, and triple integral here. Integrating is this x at here. It's the weighted x here. So x multiplied by the delta. Right? You see, this is a weighted, basically weighted average of the function, and now the function is x compared to this one, right? And that gives us this x bar, the average value or the center of the mass. Similarly, you have a y bar. All you need to do is just change this x to y, and z bar to change the x to z. Okay? Yeah. Okay, so I'll leave that z bar to you, and you can write z bar. Okay, so that's center mass. And the next one is the moment inertia. Okay. So this moment inertia now, when we're talking about the double integral, we call moment inertia. Actually, more precisely, what we called it is a second moment inertia of the area, right? Because when you're dealing with double integral, we're thinking it's a thin plate. Basically, there's no thickness, so it's just a cross section. That's right, just cross section. But now, in 3D for region D here, it's a 3D object. So this is this regular traditional definition of moment inertia now. Okay, so it's a moment inertia of a certain 3D object here. So deriving this one here is more or less the same as as that double integral. Remember, moment inertia is always about an axis. Okay. So the general formula, okay, the general formula for moment inertia is triple integral, okay, over the region D. Then we have this distance to the rotation, okay, to the rotation axis squared, okay, then multiplied by delta dv. Okay, that's the typical general moment inertia formula here. Okay, we don't know where this rotational axis is, right? But you know, if you give me a rotational axis, you want me to calculate moment inertia about the rotational axis, here's the formula. So this is basically this portion here, delta dv. That's basically it's a dm here, right? It's a small mass. So the moment inertia is mr squared, right? That's for the point mass. So you add them up, that's a total moment inertia. Okay. But we do have a couple of special cases, right? So we have this moment inertia, okay, about z-axis, okay, yeah, or about x, or about y, doesn't matter. So if it's about the z-axis, now I'm going to use this formula here, right? Use this formula. So I'm talking about distance from a point on the region D on the solid to the z-axis, right? To the z-axis here. Okay. So what's the distance from this point? The point has the coordinates x, y, z, right? Has the x, y, z here. So what will be the distance from that point to the z-axis? So here is the point here, x, y, z. And what will be the distance? Well, my drawing is, let's say for the point here, the distance to there, right? This is the distance here. What would that be? That's right, x squared plus y squared, right? Well, the distance itself is square root x squared plus y squared, but the formula here is to the power 2, so basically, so I'll call this as iz x squared plus y squared now, and then delta dv. Okay, so that's the moment inertia about the z-axis. Okay, all right, and similarly, you can derive the moment inertia about y and moment inertia about the x-axis. Okay, so similarly, ix. Okay, so you see when you're calculating the moment inertia about z-axis, there's no z here, right? So I guess when I calculate the axis, there's no x, so that'll be just y squared plus z squared, and iy will be x squared plus z squared delta dv. Okay. So that's the three moment inertia here. Okay, three moment inertia. And yeah, this is good enough. Okay. Now let's take a look at examples. Any questions? Okay, all good. So let's take a look at one example. Okay, we're not going to go over all those applications here, so I'll just use an example on calculating moment inertia here, right? Okay, so here's an example here. First, let's draw the solid here. Okay, so we have a solid. The solid is constructed by two surfaces. One is z equal to b. The other is z equal to a x squared plus y squared. Right? Yeah. So let me draw it here. Okay, so what is z equal to b? That's what? That's a plane, right? That's a plane. And what's z equal to a square root x squared plus y squared? We studied this in last lecture. It's a cone, right? It's a cone. Yeah. So the value a there basically determines how wide the cone is. Okay. All right. So we draw the cone first, and that cone will be intersected by the plane. So basically, the top of the cone here, right? The top of the cone is the plane. So in other words, this point, or the center point here, will be value at b. Okay. Yeah. Okay. So here is a solid. What I want is I want Iz. So I want to calculate the moment inertia about z-axis. Right. Yeah. All right, so now let's see, assuming the density here is 1, okay, to simplify the situation. It's constant density. Okay, so write down the formula for the Iz first, which is x squared plus y squared dv, right? So delta equal to 1, so the delta is gone, so just dv here, right? Okay, so now the question here is, if I want to evaluate, basically boils down to the evaluation of this triple integral, right? And then the first question you should ask yourself is, what coordinate system shall we use to evaluate this triple integral? Cylindrical, right? Because you do have a circle here, right? Yeah. You want to use Cartesian, it'll work too, right? But maybe it'll be more difficult to calculate. Okay, so we're going to use cylindrical here, right? So if you want to use cylindrical here, cylindrical coordinates are theta, z, right? The order of the integration generally we use we do is dz first and dr and d theta, right? But that's not the only way of you can do it. Okay? Yeah.
Where did the square root sign go?
Come again? Oh, where did this square root go?
Yeah.
Oh no, there's no square root here. You mean this square root here, right? That's the solid here. This one here has nothing to do with the solid here. This one here, it's just because of the formula for the moment inertia here. Okay, so calculate the moment inertia. That's the general formula. That square root that you're talking about will show up when we're dealing with this d at here. Okay. So the order, okay, really you can do different orders here, but let's do the dz, dr, d theta, right? So in my lecture notes, I did give you a couple of options as to different orders. Okay, so if I wanted to do dz, okay, this is the order I'm going to do here. And the first step is, what do? You're going to sketch the shadow of this objects, right? The shadow is going to be in the xy plane. Okay, so let's sketch the shadow here. In this particular case, the shadow is basically the circle here. Okay, it's a circle. Now you need to know this. You may need to know the shadows equation. So the question is, what is the circular equation? Yeah. So where this guy from, right? This is the intersection of the plane z equal to b and the surface a x squared plus y squared, right? That's the intersection between these two. So what do? You basically let this quantity equal to b. Okay. So if you let this quantity equal to b, so what we have here is a x squared plus y squared equal to b, and that gives us x squared plus y squared equal to b over a squared. Right? Yeah, very good. Okay, so once you get this information down, then the next thing is to go over the 3 steps to find the limits, right? First step, okay, find the limits for the z. So we starting from anywhere in the shadow and going up, okay, and you'll bump into the solid. Okay, so the first contact, second contact, give you this z mean and z max. So first contact is where? It's on the cone, right? Second contact is the top surface, B. So I guess now I can put down this layout here. Okay. Well, I guess before we put on layout here, there's one more thing I guess I need to deal with. I'm dealing with this cylindrical coordinates, not Cartesian. So I need to transform this x squared y squared into this cylindrical coordinates r theta z, right? So in my particular case, it's very simple. X squared plus y squared, what's that? That's basically r cos theta squared plus r sin theta squared, which give you r squared. And dv is r dr d theta, and then there's dz here, right? Yeah. Okay. So that's the setup for the dv, setup for the r squared. Then let's put down this limits for the z. Okay. So we said z first contact is this cone right here. So first contact z mean is the cone, which is a x squared plus y squared. Right, that's first contact. But I'm using cylindrical coordinates, right? I cannot substitute this one to this lower limits here. So again, what do? You change that x and y into this cylindrical coordinates. Okay. So what would that give you? A r, right? Would give you a r. Okay. So the bottom here is a r. Top is b, so that's good. Yeah. That's it.
Can we change the r into b over a?
No. Yeah. Well, right now, see, where did you get bumped into? Here, right? What's the r at that location? This portion is r, right? Is that r b over a? No, right? Which portion of r is b over a? When you're over here, right? Yeah, that r anywhere, that r is b over a. Okay? Yeah. So second one is to determine the limits for the r, and what we do, yeah. Yes, density is, but right now I'm assuming density is 1, so that's gone. Okay. So the second step, you draw a reading lines of this shadow here. First contact give you r mean, second contact give you r max. So r mean is 0, and r max is the boundary here, and the r max is this guy, right? This guy. Now this time, the B over A shows up. Last step, you sweep this reading line here across the whole shadow, right? So 0 to 2 pi. Find the limits for the theta. Okay, so that's the setup. And this definitely looks much easier setup to calculate this integral here, okay, than the Cartesian coordinates. All right. So if you do this calculation in here, let's see, inside here, there is the r square has nothing to do with the integral. So we're integrating the dz first, okay, dz. So that gives you the b minus ar. This r squared, this r here, so r cubed. Okay, be very careful doing these calculations, okay? Yeah. All right, so then do this one here, and 1 over 4 b r to the power of no 1 over 4, yeah, that's right, 1 over 4, right? Minus 1 over 5 a r to the power of 5, then 0 to b over a d theta. Okay, is that right? Yeah, sorry. Yeah, go ahead.
Wouldn't that part just up one? Would that be? Would there be an r to the 4th there? Because there's r squared dz r dr at the top. So you have r squared times r becomes r cubed.
Yeah, this guy.
And then you integrate. Oh, you pulled that. Never mind.
Yeah. So first we did dz first, right? Yeah, we did dz, which give you this one here. That the r squared r is the r cubed here. Yeah. Yeah.
For your limits of your second, shouldn't it be b over a squared?
No, here, x squared plus y squared equal to this one. That's the circle, right? The radius is b over a. So this side is r squared. Yeah. Any other questions? All good? Yeah. Okay, so I think that's what it is. This here. So now, if you plug in all these numbers, okay, we should get. So this integral here, actually, this can be taken out because there's nothing theta here. There's no theta here, right? So that 0 to pi just gives you 2 pi. So really, you can just have to calculate this portion here. So that should give me pi b to the power 5 over 10 a to the power 4. Do a little simplification, though, huh? A little simplification. So, for example, if you put this b over a over here, what was that? That's b to the power 4 divided by a to the power 4. So multiplying the b to the power 5. That's where that comes from, right? Okay. Okay, so that's the moment inertia of this solid, okay, with respect to the z-axis. So what if you decided to do a different order? Let's say, what if you decided to do r first, and then theta, and then z? How would be the layout of this layout of this triple integral here? So let's say if you're gonna decide to do this dr, d theta, and dz order. Yeah. Can you give it a try?
Sure.
Yeah, go ahead. Well, oh, I give it a try. I don't need to give it a try. I already had tried. So, the question here is always bearing in mind is you're doing this sweeping. Basically, it doesn't matter which order you do, right? In the end, you're trying to basically go over this solid D, or you're trying to generate this solid D there, right? Yeah. So if I decided to go with a dr, here is my solid here, okay? Here's my solid. Okay. So you see, previously when we did this dr here, we're starting here, we draw a line here, right? But now this time, because you're going dr first. So now you're not going to go from here now. You're going to pick any point in the solid, maybe from here. Then you started to draw a reading lines out of it. Okay, right? So that's where you draw it out. So you draw it out here. Where is R now? So you find the first contact between this line and the solid, which is here, right? And second contact, which is here. So the first contact give R mean, second contact give you R max. Okay? So essentially, the first step, what did we create? We create a segment of a line here, right? Create a line here. So we create this portion here. So in other words, my R, it will be 0 at here and end up over here, right? End up here. Now the question is, when I end up here, what will be the distance? So that's going to be my R max, right? That'll be R max here. So where did we start it? We started arbitrarily anywhere along this XZ axis, right? So we started where? We started this portion here will be indicated by Z, right? So we started at Z, okay? And we draw the reading lines out of it, basically that line perpendicular to the Z axis. So here you have a right triangle here, right? Your right triangle. So how do I get to the R then? That has to be based on the cone equation, right? See, this cone here is this, right? This is a cone here, okay? So what will be this? What will be this R now? This is my R here, right? R max, basically. What will be the quantity for this R max? Can you see that? Just R? No? Come again? Z over 8, exactly, right? Z over 8. See, the second point is where? It's on the surface, right? It's on the surface here. So basically, this surface here in cylindrical coordinates, it's AR, right? It's AR, okay? And where is it? It's a Z at here, right? It's a Z. So the R is actually, okay, is Z over A. So this is surface Z, right? This is Z equal to this, okay? Z equal to this. So the R max is Z over A. Okay. Then you have our same integrand as before. R squared at here, dr first, right? And d theta, there's another R here. So R dr d theta dz, that's what we're going to do. Okay. So first, when you create that line, right, this line segment has minimum 0, maximum Z over 8. That's general, right? That's general. Second, theta. So what do we do? So the theta here is we are trying to create this solid. So what we do is we're going to basically sweep this one across this whole region, right? And look at this mean and max of theta sandwich this region. Yeah.
Wouldn't the moment be 0 about the z-axis since it's all symmetrical?
Not necessary. I don't think so. Is there anything? No. Moment inertia, not because it's symmetrical, you will get a 0 moment inertia, right? You see, you know, figure skating. So for figure skating, guys, how does a girl slow herself down or to make herself spin faster? Yeah, so they, you know, when they try to slow down, okay, never gonna get a 10 points. So you know, they slow themselves down, right? So why? How they slow themselves down? Because you created sort of geometry-wise, right, wider. But when you do this, right, and you're becoming faster because the moment inertia in this way is smaller, right, and it's symmetric. Yeah. Is that good? Yeah. However, okay, there is a case it's going to be 0. That's when you have a very thin bar, cylindrical bar. Basically, let's say for example this pen here, right? If you consider this pen as a very, very thin circular bar, then the moment inertia about this z-axis, which is the axis going through the cylindrical object here, you consider that as 0. Okay? Yeah, basically the r, the distance, right? You consider it as the cross-section is so small. Okay? Yeah. So r max is done. Then theta, that'll be 0. So basically sweeping 0 to 2 pi, right? Okay. So the second step, what did you create? You created a disk here, right? A disk. So the last step, you sweep the disk up and down. So up and down across the whole region, which basically means the z will go from 0 to b. Okay. So this whole process right here creates the solid D without any redundancy and without any overlooking of any corners of this here, right? Yeah. So that's the nature of this integration. All right. Any questions? Yeah.
If we start with theta, then
If I started with a theta, then what?
how many approaches?
Theta and r. Good point. So let me see if I have the case set here. Why did you always want me to try? Why didn't you try it here?
I'm a midterm. I'm very easy.
Come again? Sorry?
You have a midterm, you said we.
Oh, you have a midterm. That's a good question. I don't have the answer here yet, but let's see. If you start with a theta, then what? Maybe if you start with a theta, how do you create that thing? I need to think about it. How do you create the solid starting with the theta? You got me there. I don't. You know what? Anybody can think of a way of creating a theta first, creating the solid here? Because the theta is more of like a dependent thing, right? It depends on a previous action. Then you can create things. It's like invisible at the beginning. So how do you create a theta first, huh? Yeah. Okay. Create a shadow somewhere else. Okay, let's keep it as a question then, huh? Good point. Yeah. Because usually, when you create something, then you rotate, right? You'll create something else. So you can't rotate nothing, right? Huh? So anyway. Any questions other than this one? Yeah. Okay, now let's talk about the new topic. Vector field. Okay, so now we have a double integral, triple integral now, okay, and we're basically equipped ourselves with enough knowledge here with the partial derivatives, dot product, everything. So essentially, what's coming here, right, for the next maybe 6 or 7 lectures until the end, that's actually where most of the question coming from for the final exam. Okay, yeah. So vector field is actually not new. What we learned here is we learned that we can have a vector, right? Now this vector f, maybe it's a function of x, y, z. So this is not a scalar function. This is basically, this is a scalar function. This is going to be a vector function. So what happens is, this function, okay, has three components, like a euro, okay, so m and p, okay. But each one of the component here, they're functions, okay, they're functions, and they're functions of coordinates x, y, z. So this is basically a so-called vector function. So this vector function, if I plug in different values x, y, z here, right? If I plug in, I will get a value here, 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 right? Yeah. And basically, if I plug in different x, y, z, I get a vector. See, right? Yeah. But if I plug in different x, y, I get a different vector. So now if I plot each one of the vector in the 3D space, right? Imagine what happens is you create so many vectors, and you basically, so where you let's say I have x naught, y naught, z naught, okay, plug in there, I got a vector f1, for example, right? And you plug in x1, f naught, let's say, y1, z1, you get f1, okay, another vector. So you draw the vector at that location, so you draw as many as possible, so in the end, right, you end up yourself with a kind of a drawing of so many vectors. That's called basically a vector field, okay, vector field. Okay. So this is a very, very useful application tool in many areas here, okay, vector fields. I'll show you a couple of them, but before that, I'll show you a couple of the typical vector fields here. So this is called a 3D vector field. Okay, so this will give you a 3D vector field. So if I only have two variables here, so then I'm going to get a 2D vector field. Okay, so this is a 2D vector field. Okay. So for example, maybe a very, very simple case. So let's say f equal 1, 1. What is that? That's a vector, right? That's a vector. And at the same time, it's also a vector field. Why is it still a vector field? Which means doesn't matter where it is. So here is xy coordinates. Okay, xy coordinates, right? At the 0 point, there is a vector which is 1, 1 associated with a 0 point. So that vector is what? 1, 1. So that's 1, 1. Let's see, right? Is that right? And at let's say at 1, 1 point, at x equal to 1, y equal to 1, I have the same vector, which is 1, 1. So I have another one here with the same magnitude, same direction, like this, right? So it doesn't matter where, basically, you have, okay, this is so-called basically a constant, right? A vector field. Okay. It's all pointing to the same direction at anywhere in the xy plane, and with the same at anywhere in the x plane at the same direction, the same magnitude. Okay. That makes sense? So that's a constant basically here. And if I have a different ones here now, it's not a non-constant one. So f equal, let's say x I hat plus y j hat. All right. So so this vector field is a function of x and y now. With different x and y, this vector will be different. So now if I draw this one here, so I would get is actually this one here. So why is this going to be this vector field? So let's take a few examples here, right? So let's say if I plug in x, y equal to 0, 0. So I don't have anything there, right? But if I plug in x, y equal to, let's say 1, 1, which is basically at 1, 1 point. This is how you draw this vector field here, okay? So the vector field you draw is, you draw the vector, starting point is the xy or xyz. So at 1, 1, here's a 1, here's a 1, okay, here's a 1, right? Draw the vector. So plug in 1 and 1 here. The f equal to 1, 1. Okay? So draw the vector starting from here. Draw the 1, 1. Okay? 1, 1 basically it's the magnitude. It's this vector basically, but then you move that parallelly to here and then you draw it, right? So that's how you draw this vector here. So it's like this one here, right? It's like this. But if xy is coordinate is 2, 2, so that vector basically becomes 2, 2, right? So the same direction, but the length is twice as much. So that's why what you draw here is this. If this is 2, 2 point, so you draw the vector with the same direction but twice the length as this one. Okay? Yeah. So that's how you draw this vector field. So same that you plug in this one here. So it's a radius vector. So this vector actually is more of a vector of electric field, right? When you have a charge, the particle, okay, then the charged particle has this electrostatic electric field. Okay. So similarly, let's see for this one here. If I have f equal to f equal to y I hat minus x j hat. Okay. F is a vector. So for this particular vector, if you do the same thing, you do the same thing, basically plugging the points and draw the vector field. So what we end up with is, you look at this one here, what's this vector field? It's like a rotating fields, right? Rotating fields. Basically, it's more like a pond or a water in the sink. When you let the water go, it's like depicting this rotation speed of this water. That makes sense, right? Yeah. As you go outside to the atrium in a courtyard there, right? There's a hole in the middle. So when the water is flowing, the motion of the water is basically like this. Okay. Yeah. So this is a rotating field. Now, if you change this one to negative y, so this is this, okay? Negative y I hat plus xg hat. So suppose what's going to happen? Yeah, it's going to be a different direction, right? So this is a clockwise, and this is going to be a counterclockwise, okay? Right? So that's basically how you get the vector field. So take a look at the lecture notes on using Maple to draw those fields. MATLAB can also do the same thing, and the MATLAB is a quiver command so that you can draw those vector fields. So those are 2D fields, right? And this is a 3D field. And for this particular one, this field is, let's just be correct here. So this field is this. If I have a function f x, y, z equal to x squared plus y squared equal to z squared. So this is a function of this, right? And if I calculate this gradient of this function, what do I get? I get 2x, 2y, 2z. Okay? Yeah. So if I plot this one here, this is a vector, right? This is a vector. This is basically like a vector here. If I plot this one here, that's what we get. Okay, that's what we get. So this is more of like those needles pointing out from the center of the origin there. It's like a porcupine's back, right? Yeah. Okay. The other examples you can see this is a sort of experimental results here from textbook. So you have an airfoil. Okay, you place that in the wind tunnel, right? Then you blow the constant maybe velocity of wind to it. Then you put some kerosene for smoke. Okay, and then you take a picture of this. So you will see that the flow of the wind, okay, changes around this airfoil, right? So why do we study this? They're basically sort of aerodynamics, and different shape or different speed will give you the so-called different lifting force, right? Yeah. So as a matter of fact, what we're going to call this a line integral, vector line integral, I'm going to show you here, is directly related to this so-called lifting force. Okay. So as you can see, those lines here, okay, those are so-called streamline. Okay. In the in MATLAB, you do have a command to draw streamlines. So for example, if I have vector fields of this or this, right? So streamline basically is starting anywhere. Okay, this is basically the so-called streamlines. Okay, streamlines. And the arrows here, basically the arrows vector, okay, tangent to the streamline, and the magnitude has something to do with the velocity, the flow. Okay, either it's wind or fluid. Okay, doesn't matter. So next term lecture, fluid mechanics, is when it's called fluid mechanics. It's actually not necessarily it's fluid, right? Okay, so now we understand what a vector field now. Okay, so the question is, what do we do with vector field? There are a couple of things. Number one thing that we're going to do is do this: vector line integral. Okay, vector line integral. Yeah, I've been teaching 248 for many years. I find 248 probably will be more applicable in your future courses than 246 for both for all three programs. Okay, yeah, somehow. So for 246, more useful for electrical mechanical, but 248, it's a very foundational course for all three programs. Particularly for electrical, the third year electromagnetic, the principal course, right? You know, the first few lectures is basically what you just learned here. Okay, vector line integral. So I'll start with a very simple scenario here, okay, and then we'll talk about what the vector line integral here is. Suppose we have a mass that here, we apply a force to the mass, and then we move this mass by a distance of d. Okay, we move this by d. So this force applied horizontal direction, right? Horizontal direction. So tell me, how much force, how much work did it do for this force? When you push this one by distance d here, the work it does is force times distance fd, right? Fd. Okay, so now if I change this direction of the force like this and move through a same amount of a distance d. Okay? Yeah. So now how much force did it do now? How much work? Yeah, let's see, this is theta here. So pardon me? Yeah, F cosine theta d, right? F cosine theta d, well, let's say I use vector concept here. Okay, vectors. If I use a vector concept here, I guess I'm not going to use this fd now, so what should I use now? It's absolute f, absolute d, cosine theta, right? And what's this one here? Dot product, yeah. So this is f dot d, right? F dot d, okay? So that's very simple. That's basically you move this much here with this direction, with this little distance, you get that amount of force. So now let's think about more sophisticated case. So let's say suppose you're moving along a certain curve C, like this. So it's not a straight line. It's a curve C in 3D space, which is described by a parametric equation R, right? Parametric equation R. So you're moving the mass around here. And the force, I can think of the force that is here as if there is a vector field. Okay, there is basically a vector field, okay, in the 3D space. Okay, yeah, is that good? So essentially, at anywhere along the curve, right? Anywhere along the curve, you have an associated vector. So you can call this as a sort of a force field, right? You can call this sort of force field. Okay. So anywhere along the curve, there is certain force with pointing to certain directions. Okay. So then the question here is, how much force how much work will the force field do to move the mass, okay, from here to there, right? So that's a more general question now, right? And not just moving a small distance, you're moving along a irregular curve. And at anywhere along this curve, there might be a different amount of force. Okay, the force may be different because of field. Okay, yeah. So then, what does the W equal to in this case here? Okay. So this one needs basically, whenever you see this kind of question, it needs an integration essentially. Integration always starts with an infinitesimal segment. Okay. So let's say you take a very small segment here. So let's call this segment ds. Basically, you're thinking I'm moving through a very short distance ds, right? Very short ds. It's like a d here. Now, we're not going to use the ds here because you see the displacement, right? Displacement is a vector, so I'm going to use a ds vector. Okay? So that's a small displacement vector. So because it's a very, very small, so maybe it started here, ends at here. So where you started, there might be a certain vector force over here, right? There might be a force here. And because it's small, so where it ends, we're gonna assume that the force not gonna change, okay, with this small ds. Is that clear? Right? So that means what? That means my dw, okay, just basically the force, the work that does through this small ds here, according to what I have here is, so that'll be F dot which one? ds, right? Yeah. Okay, dot ds. Okay, good. Okay, so this F, that's okay. That's basically the force field, right? You know, you plug in the coordinates at this point, you will get that. So that's going to be known. So the question here is, how do we do with this ds here? Well, ds is a segment of a line at here with a certain direction, right? Displacement. So this the distance, that's okay. That's basically where it is. So how do I depict or describe the direction of the ds? What should I use to describe the direction ds? Tangent vector, right? Tangent vector. Yeah. So the ds here, basically the direction of the motion displacement, that's basically the tangent direction of the curve. So I can use the t hat, which is the unit tangent vector, right, multiplied by the segment of the distance or the length. Now this time I can change the ds back to this regular, the vector ds to the regular ds now. Okay? Yeah. Okay, so sometimes some textbooks instead of they use this dl vector. Okay, so this is so-called a differential. Okay, this is called a differential segment. Okay, so differential segment not necessarily it's a scalar now. Okay, when you look at a differential segment in 3D space or even just 2D space, it's actually a vector, right? Yeah, basically where it points to. Okay, so now I have dw equal to this now, right? So this is only the work does through this little segments here. But we're going from here to here. So what do we do? The total is just integration. Okay, so integration, you get f t hat ds. Now where are we integrating? We're integrating over where? Over this curve C. Okay. Yeah. Now that's basically the total work the force field does when moving this mass through this whole curve. Okay. Well, back to this simple mathematic meaning here, you know, this has nothing to do with force or work. This one here is basically called a vector line integral. Okay, this is basically a vector line integral here. So this simple mathematics equation here actually can be used in many different applications. Okay, many different applications. For example, let's say if this F here not necessarily is a force, if this F here really represents is the velocity of a flow of a fluid in a pipe, That's okay, right? That's okay. So when the fluid is flowing in the pipe and the velocity is different, maybe at a different location, it points to the different direction, right? So now what we wanted to do is we want to say, okay, how about calculating? So you have, let's say you have a velocity flow of fluids, okay? Then you have a certain kind of a curve. Okay? So what we want to calculate, let's say this is a v here now, right? Let's use a v here. Okay, velocity, representing velocity of this. So we want to calculate the vector integral, okay, basically v dot this t hat and ds over this c here, right? That's a vector. And this calculation here, okay, is a vector line integral just same as this one here. Now when you calculate this one here, this is so-called circulation. So this is basically sort of fluid dynamics here. This is a circulation, okay, along the curve. Okay, circulation of the fluid. Okay, along the curve. All right, yeah. So the circulation around the curve, the fluid on the curve here, and the unit for this one, okay, velocity is meter per second. So the t hat ds is a differential line segment. So the overall this unit here is actually L over a time, L square, sorry. Okay, it's actually L square over time. So time can be seconds, can be hour, right, like this. Okay. Yeah. So this is more fluid dynamics here, okay? Yeah. There is a theory you probably will learn in the future. This is basically, I'll short it as a Kg theorem. Okay, Kg theorem. So this circulation here, in a lot of textbooks, they use a gamma, okay, to represent this circulation in the fluid, okay, along the curve. Okay. Then remember the picture I showed you at here, right? Showed you here. So where people may be interested is the lifting force, okay, on the airfoil. So if you use L, yeah, the L here is not the length. L here is the so-called lifting force. So that lifting force L is actually equal to rho, V, and gamma. So rho is the density of the fluid. V is the relative velocity between this airfoil and the flow of the fluid. Let's see if your airfoil is static, then that's just the flow of the fluid. And the gamma here is this quantity here. Okay? Yeah, this quantity. So anyhow, just take a look at this. I'm not going to talk about this, but you can see this is one application basically of this circulation, okay, or the vector line integral. Any questions? Okay, yeah, good. Okay, so now the question here is, how do we calculate the vector line integral, right? How do we calculate this thing here? So now you look at this one here. First question should be, what do we know? What do we not know? Do we know f? Well, chances we know, right? It's probably going to be given. How about the t hat? Where's the t hat going to be given? Yeah, t hat is the tangent vector what? The curve c, right? So if the curve c is given, which is r vector, so then how do I calculate d hat? dr over dt, right? And then normalize that. So how about this ds here? What's the ds? ds is the line segment. Have we derived the equation for the ds? Right? Yeah. When we were learning the arc length of a certain curve in 3 space, we derived. So basically, all of these things here we already know, right? So the equation, we can rewrite the equation now. Okay. I'm gonna basically rewrite the equation of this vector line integral. Okay. And this, I'll use f here, okay, dot t hat ds. Okay? Yeah. Okay, so f, we're not going to change that. That'll be based on the question. And t hat is dr over dt, normalize it. Right, that's t hat. ds is what we learned, arc length, which is r prime dot r prime, right? Yeah. So this is dr over dt dot dr over dt. And in the end, there's dt. So this whole chunk here, that's ds. This is t hat. Okay, yeah.
Isn't tangent double derivative of RT?
Come again?
Isn't
Oh.
tangent double derivative of RT?
No, not double, single. Just first derivative.
So the normal one is double derivative?
A normal one is dt hat over dt, not just the second order derivative, right? The normal, you mean the normal n hat, right? Yeah. Normal n hat is a dt hat over dt over absolute value dt hat over dt. Yeah. Okay? No. Okay. So this actually can be simplified here, okay? This can be simplified. So you see, this dr over dt dot dr over dt and what was that? That's basically, see the dot product, right? The dot, it's the dot product dot itself. That's basically okay. This is basically absolute value dr over dt. Okay. Yeah. So you know when you a dot b, and sorry, when you a vector dot a vector, give you what? Give you the absolute value a squared. And in the square root, the square is gone, so that's just absolute value itself. All right? Yeah. So they say then now you have this quantity, the same thing, right? So this gone. Okay. So you end up with f dot dr over dt and dt. Okay? Yeah. Was that clear? Yeah. So you can simplify one more step. You can get rid of the dt here. Okay? But getting rid of the dt doesn't mean that you won't have the dt, because when you take a dr vector, this r is a function of t, right? So it's a dr itself. This is a differential. This is a derivative. So when you take when you have this parametric equation and you take the differential, you'll have the dt back. Okay? Yeah. So really, you can stay with this equation. That's enough, right? Yeah. So calculate derivative, calculate dot product, and do the integral, right? Of course, you need to find the t range. You know, generally that depends on the parametric equation. Okay? Yeah. So, any questions? All good? Yeah, I think the calculation of this line integral is very straightforward here. Okay, it's fairly straightforward. So let's take a look at a quick example here, right? Yeah. Suppose that I have a vector field yz, xz, xy, and then we have a curve. We also have a curve C. Okay, so that's the curve C. And, let's calculate this. Let's calculate this line integral. So maybe I'll write it down here. Save a little writing. Yeah. Okay. Okay, so instead of jumping into it here, you calculate some of the quantities first, and then you plug it into it, right? Yeah. So first thing is, you're integrating this f dot this guy here, right? And where are you integrating? You're integrating over this curve C. So what we're going to do is we're going to have to replace those x, y, z here with the corresponding x of t, y of t, z of t. Because this is a field. Basically, this field is everywhere. But you don't care about the field anywhere but the location along the curve C, right? So this f at here, okay, actually going to be plugging these quantities into this. So it's going to be what? Y, z, it's this multiplied by this. X, z, x, y, right? So that's your vector field, right? That's the field along the curve C. And then dr, or maybe just calculate dr over dt, doesn't matter. So this dr over dt, okay, that comes from this derivative of this vector, derivative of the parametric equation. So that's very easy. So 1, 2t square, 2t, 3t square. Okay? So now you have vector of this, vector of that, dot this two vector, right? Dot the two vectors. So this dot this, that equal to t5 plus 2t5 plus 3t5, which is 6t5. Okay? And then you do the integral. So the integral is integral over the C. And t, you're integrating from where? 0 to 2. Integrating what now? Integrating the 6t5. T. Okay? And that's very easy. Okay? That equal to 64. Okay? The key step here is make sure you do the substitution for the vector field f, right? And do it right. Otherwise, your calculation won't be right. Now, here's one way of calculating this one here, right? Now, there's a slightly variation in the formula. There's a slight variation formula this. Because this f equal to m n p, okay? This is your vector field f, and it has maybe 3D space, has three components m and p, right? So in this particular case, like m and p like this, okay? Then if I plug in this dr, maybe it's x of t here, y of t, and z of t, okay, dr. So if I plug into this equation here, okay, let's see what happens. So the line integral, vector line integral equation is this, okay, is this, right? Yeah. So then dr, sorry, this is r, right? Dr is dx, dy, dz, and then dt, okay? Yeah. This is dr. Okay. So then when I multiply or do the dot product that here, so it's this vector dot this vector, right? It's this vector. Okay? Yeah. So what do I end up with? Hang on a second here. No, there's no dt here. Okay, there's no dt here. Differential, just dx, dy, dz. Depends on the x, the function x, you'll have the dt out, okay, dt back. So if I do the dot product of this one here, so what I'm going to end up with this c m dx plus n dy plus p dz, right? So you end up with this an alternative, basically, formula for this calculating the vector line integral. But using this formula here, there is a tendency of making a mistake here, though. Okay, a lot of people when they use this mistake, using this formula here. For example, if this m is this, m p, right? Is this in p? So you might make a mistake. Is this is c, m is what? Is y z, right? And dx plus n is what? Is x z, right? And p is xy. Okay, so you plug in like this, right? You plug in like this. So then you start to calculate, oh look, this is dx, I'm going to integrate with respect to x, integrate y, and it's not like that though, huh? It's not like that. So what you need to do is you need to plug in this yz with your parametric equation. You still need to calculate this dx of t according to the parametric equation. Okay, so this is your x of t. y of t, and z of t. All right? Yeah. So you still need to go over the same thing here. Okay? It's not integration of x, integration of y, or integration of z here, right? Yeah. So that has to be very careful though. So let's take a look at one more example here. Okay. So I'm going to use this formula to do the calculation, all right? And we'll try a 2D vector field. Okay. So this is the vector. And this is the parametric equation for the curve C. And to calculate the line integral. If you plot it out, this is what it looks like. This basically. So here's a vector field, and here's a curve C. So you go from here to there, right? And we're interested in the circulation of the fluid along the curve C from here to here, right? Yeah. Okay, so if I use this formula here, for 2D, you only have two terms. Okay? So if you plug in the value, negative y dx plus x dy, like this, right? But you're not integrating with respect to x and y. So what's going on next is, you're going to replace this y with t squared. Okay? And then you're going to take this differential dx, which is basically this quantity here. Okay? Dx. So x is t, so dx is basically dt, right? dt. And x is t, so plug the x of t here. dy, y is t squared. So d t squared, right? dt squared. And dt squared equal to, what does dt squared equal to? 2t dt. Don't forget the dt, huh? Yeah. Integrating over the c, integrating over this t, 0 to 2. Okay. So overall, you see, here's the t, 2t dt. So that's 2t squared. 2t squared dt, right? First one is negative t squared, so together it's basically just t squared. So, okay, yeah. So that's a very simple integral, and which equal to 8 over 3. Yeah. So either formula works fine, depends on which one you're more comfortable with, right? But if you choose to do this one here, make sure you understand that you're not integrating with respect to x or y, because in the end, it's an integration with respect to the parameter, the common parameter t, okay, or anything the question gives you. Okay, so let's look at an easy one here. This is very easy. This doesn't really need a calculation here. Let's just look at this question here, right? F equal to x, y, okay. And the C is x squared plus y squared equal to a squared, okay, counterclockwise. Okay, so basically, I'll use the circle here. Basically, the C here is a circle, right? Here is a circle. So here's a circle, and F is a vector field. So C goes counterclockwise, okay. And F is a vector field. And we're interested in this F dot dr, the circulation. Okay, the circulation. Is that good? Yeah. So this question actually doesn't need a calculation. From the geometry or from this definition of this circulation, you will be able to end up with the results here. The question here is, here's a vector field. Here's a dr. And it's probably better to go back to the original definition of the line integral, which is what f dot t hat ds, right? T hat ds. So the t hat, you should understand, is a tangent vector of the curve. Okay. So let's see, if I have a point over here, the tangent vector is a tangent, right? It's tangent. So at anywhere along the curve here, according to the vector field, where does that point into? So if this is xy here, right? This is xy.
Perpendicular to it?
Exactly. Your vector field is perpendicular to that. So this is your f here, this is your t hat, right? So for this vector field. So it really doesn't matter where you pick the point. Anywhere along the curve, that field f is always perpendicular to this tangent vector t hat. So yeah, if two perpendicular vectors dot each other, it's always 0. And you're integrating a 0 all across the whole curve, it's still going to be 0, right? So this one here, from the geometry of these two vectors, you save yourself the calculations there, all right? Yeah. Any questions? All good? Okay, so you can try if I change this one to negative yx. Okay, apparently it's not going to be perpendicular now. And what will be this one here? Okay, try it out. Okay, any questions? All good? Yeah.